morning. So finally I'm coming to this week's recording. So the first one is about the abstract vector spaces. So why do we need more abstract concept for vector spaces? Let's go back to the linear equations. So we learned in the last week, or you knew it before, that you can write every system of linear equations in the form of a matrix times the column of vectors, the column of coordinates of the vector. And the easiest way is the homogeneous equation where the whole equation has got this form. So it looks like the one-dimensional case, so some scalar times unknown number equals something, and then you can compute the scalar. With the matrices it's more complicated, and we learn that the key notion there is the linear dependence. So the number of free parameters in the solution space is given by the number of linearly independent rows and columns in our matrix, right? So that's last week's story. And imagine that you have got the homogeneous system, and then of course the sum goes to a sum of the products, and therefore it's zero as well, and the same with a scalar multiple. So the solutions of our system of equation, which might be handling say 1 million of coordinates x, I, so big data, but if there are say not 1 million of independent equations but 2 less, then the result will be having 2 free parameters, and it will be in some sense two-dimensional, and we want to understand this in an abstract way. And therefore we simply talk about vector spaces, and what we do is we simply completely copy the properties v1 to v4. And if you remember, it was just the fact that there was the addition which behaved like an abelian group, so a commutative group, so it's commutative and so on. So there is the scalar multiplication, maybe instead of the so on as well. So the addition is commutative, it's associative. So it doesn't matter in which order I do the addition. There is the scalar multiplication, which is distributive, right? So it's c times u plus v equals c times u plus c times v, and also the other way around. So b plus c, so that's 2 scalars times u equals bu times c plus cu, and one more was that 1 times u equals u. So we are dealing with a field of scalars. So the scalars are in a field, and there is the one, and we request this, right? So all these properties were absolutely obvious once we dealt with the n-tuples of elements from a field, right? Because it was just all obvious coordinate wise. But now we want it as an abstract definition of what is vector space for us, right? So that's the new thing. And we learn very quickly that once you use abstract axioms as those, then the other obvious things from the example we had before, just the coordinates in an n-tuple, we have to prove the other obvious things, like for example a times u is 0 if and only if one of them is 0, or if 1 times u is u, then minus 1 times u is minus u, and all these has to be checked carefully, right? And this is what we have got here. So just from the axioms we deduce the other properties. So, and similarly, the linear dependence or independence is just taken over from what we did already with the n-tuples of scalars, except now it's just a matter of definition. And look how we do it. We say that an k-tuple of the vectors v1 through vk is linearly independent if the only way how to get 0 via a linear combination is that all the a's are 0. Once we deal with a field of scalars, this is equivalent to the fact that if they are linearly dependent, then it means then one of them can be computed as a linear combination of the others, because we pick up the A which is non-zero, push all the others to the other side, and then divide by the A, right? And because we are over field of scalars, it's always possible. So we say that the bigger set M is linearly independent if every k-tuple inside of M is linearly independent. So in particular, an empty set is independent just by the very definition, because the condition is empty and therefore fulfilled. Right, this way we can then talk about generators and subspaces, right? A subspace in a vector space means we have a subset where the operations of scalar multiplication and addition of vectors is closed. So we don't jump out of the subset if we add two vectors or rescale the vector by multiplication with scalar. And in this way we can then talk about a subset generated by a given set. So you see, if you take any subset M, you can simply take what we call the span or linear span of the subset, and that means we take absolutely all the linear combinations which are there. So what is the span of an empty set? It's just one point set 0, right? Because of course we have to have something to be a vector space, so the 0 is the smallest one. So essentially the better way how to define it is not to say that you take all the linear combinations of whatever you find in M, but you say that M is the span of M, so the linear span of M is the intersection of all the vector subspaces which contain your set. And in this case you end up with the right answer for the empty set. It will be 0, right? So that's this. And then we come to the very essential concept, and that's the dimension and the basis of a vector space. So we say that a vector space does have a basis if there is a subset, so that will be called the basis, which has got V as the linear span and is a linearly independent subset, right? So for example, if you take any vector, say field K, and we take the vector spaces we know already, so the n tuples of coordinates, then the bases are, for example, the vectors EI, where you just put everywhere 0, on the i's position you put a 1, and everywhere else again 0, right? So these guys, where I goes from 1 to n, clearly form a base of the vector space. If we take the polynomials in X over the field K, then of course we also get a nice set of which is a base, because you can take 1 x square, well, not x square but x, to have it in the right order, x square, and so on up to infinity. So this will mean that the basis is not finite, but it is a base because you simply know that all the polynomials will be linear combinations only of finite number of those. If you take, say, real numbers as a vector space over the field Q, the rationals, then you can't find a countable basis there, right? So then it's more subtle thing whether you can find a basis or not, but definitely it will be a much more infinite dimensional vector space than the space of the polynomial. So this should be enough for basis, and let's come back to the linear equations. So clearly if we deal with the homogeneous linear equations, then you see that the space of solutions is a vector subspace in our space Kn. So this is the original motivation, and it could be very small dimensional. So if A is an invertible matrix, it will be just the 0 subspace. If it's a square matrix but the rank is not complete, not the maximal one, then you are leaving the free parameters when seeking for the solutions, and that's exactly the number of the free parameters will be the dimension of the subspace. And you can, of course, if n is the number of free parameters, then finding the particular solutions for this choice of parameters, just taking always 1 for one of them and 0 for the others, will create independent solutions. Clearly they will be independent, and this will be the basis of the space of solutions, right? So and in general, this is nicely described in the proposition here, right? So it just formalized what I've told right now. And next, if we go to the more general case, or the completely general case of the linear equations, then of course you can notice that if we add a solution of the homogeneous one with one solution of the non-homogeneous one, we can again get a solution of the non-homogeneous one. If we make a difference of two solutions of the homogeneous one, we get a non-homogeneous one, we get a solution of the homogeneous one. And therefore we see that in order to find all the solutions, so it's just what I wrote here, we end up with the theorem which has got a name, but there are many names, so you can see here how many different names you can find in the literature for the same theorem. So there is a saying in mathematics that if a theorem has got a name, then it's absolutely sure that someone else was inventing it earlier than the one whose name is carries. But let's look at the content. So the solution of the non-homogeneous system of linear equation exists if and only if by adding the columns of B, you don't increase the rank of the completed matrix. So you just take A plus the column, and it must not increase the rank of the matrix. That's completely perfectly matching the idea that the linear maps and the matrices are roughly the same thing. So A can be seen as a linear map throwing X into the results, and we want to hit the B. And you see that actually B is then a linear combination of the columns of A. And that's the reason why the first claim is true. And if there is a solution, then the subspace of all the solution is given as one particular solution plus the vector subspace of all the solutions of the homogeneous subspace. So, right, I think this is enough for the first bit for this week. So I will come back to the next one soon.